Hey there everyone! Welcome to today's deep dive into powder metallurgy, a super efficient and versatile process that's revolutionizing how we manufacture metal components. This technique is a game changer for industries like aerospace, automotive, medical implants, and tool manufacturing. Today I'll walk you through the key stages, the materials involved, applications, and the pros and cons of powder metallurgy. Let's jump right in. Powder metallurgy is all about creating metal components from powdered materials. It's perfect for making complex shapes, cutting down on material waste, and achieving top-notch material properties. Think of gears, bearings, high-performance materials like tungsten carbide tools and sintered magnets, all thanks to powder metallurgy. The process has four main steps: powder production, blending and mixing, compaction and sintering. Each step is crucial for nailing the final properties of the component. First up, we have powder production. Metal powders can be made through various methods like atomization, reduction, electrolysis, and mechanical milling. The method you choose affects the particle size, shape, and purity, which in turn impacts the final product's characteristics. Next is blending and mixing. This is where different metal powders and additives come together to get the perfect composition. Sometimes lubricants or binders are added to make compaction and sintering easier. This step ensures uniform particle distribution, which is key for consistent mechanical properties. Then we move to compaction. Here, the blended powder is squashed into shape using a die. High-pressure techniques like uniaxial pressing, cold isostatic pressing, and hot isostatic pressing are used to form green compacts. The density of this compact is super important because it influences the final product's strength and durability. Sintering comes next. The green compact is heated to just below its melting point in a controlled atmosphere. This helps the particles bond through diffusion, boosting the component strength and reducing porosity. Advanced sintering techniques like spark plasma sintering and liquid phase sintering can take material properties to the next level. Powder metallurgy is a hero across various industries. In automotive, it's used for engine components, gears, and brake pads. Aerospace benefits from turbine blades, high-strength structural components, and heat-resistant alloys. In medical fields, it helps produce biocompatible implants like orthopedic prosthetics and dental implants. It's also a go-to in electronics for magnetic materials, electrical contacts, and high-purity conductors. The advantages are many. Near-net shape manufacturing means less machining and minimal waste. Precise chemical composition and microstructure lead to superior mechanical properties. Plus, it's a lifesaver for materials that are tough to machine, like tungsten carbide and superalloys. But there are some drawbacks. The initial cost for powder production and die design can be steep, making it less ideal for small-scale production. And controlling porosity can be tricky, with some mechanical properties like ductility being lower than with wrought materials. But despite these challenges, powder metallurgy remains a crucial technique in modern manufacturing. To wrap it up, powder metallurgy is a highly efficient and sustainable process for making metal components with superior properties. By carefully controlling powder characteristics, compaction, and sintering conditions, manufacturers achieve high precision and performance. I hope this session has shed some light on the powder metallurgy process. Thanks for tuning in. If you found this informative, don't forget to like, share, and subscribe for more educational content. See you in the next session.